The story you think you know might be missing its first chapters. We tell ourselves that humanity is the only advanced civilization Earth has ever known. That our cities, our technologies, and our spacefaring ambitions are the natural climax of a long, unbroken rise from primitive life to planetary dominance. But what if that's just the latest verse? What if intelligent life has walked this world before us, 200 million years before a single human breathed, long before mammals emerged from the shadows of the dinosaurs? In epochs so ancient that entire mountain ranges have risen and been worn to dust. This is not the plot of a science fiction novel. It is a legitimate scientific question. It's called the Silurian Hypothesis, named after a fictional race of intelligent reptiles in British television. But behind the science fiction flavor hides a serious inquiry first proposed by two NASA-affiliated scientists, Gavin Schmidt and Adam Frank. Their question was simple and terrifying. If an industrial civilization had arisen on Earth millions of years ago, could we even tell? Could we find the traces? Would anything be left for us to see? The answer, they found, is far from comforting. Imagine you are standing on the surface of the Earth 100 million years from now. The continents are in different places. The coastlines have changed completely. Cities are gone. Forests have shifted. Climates have transformed. Even the ocean floors have been entirely replaced. The skin of the Earth has been peeled back, melted, and remade over and over again. In that imaginable span of time, even the mightiest human achievements would vanish. Stone monuments would crumble to dust. Skyscrapers would twist and collapse under relentless erosion. Metal would corrode into flakes of oxide and scatter into the soil. Plastics would fragment into molecules and disperse through sediments. The surface of the planet does not keep your secrets for long. It is a master of forgetting. So, if there were once others, beings as intelligent as we are or more, they would have left behind only the faintest of fingerprints. Not cities, not monuments, not even skeletons. Just signals. Tiny anomalies locked in the rocks or frozen in the chemistry of ancient soils. We might never even recognize them as artificial unless we knew exactly what to look for. This is where the Silurian hypothesis moves from what if to how would we know? It's not about proving that ancient civilizations existed. It's about designing the test, about asking, if they had existed, what evidence could have survived the crushing jaws of geological time? But first, we need to grasp the scale of that time. Human civilization, from the first farming villages to the International Space Station, has existed for roughly 10,000 years. 10,000 years is a blink, a speck. Less than 0.002% of the time since complex life first appeared on Earth. And our industrial era, the last 200 years, that's nothing. Now, stretch your mind over millions of years. Picture the age of dinosaurs, which lasted over 160 million years, 800 times longer than humans have been around. Picture the Carboniferous swamps, the Cambrian seas, the alien landscapes of the Silurian period, worlds separated from us by hundreds of millions of years. In all that time, could intelligence have arisen and vanished without a trace? The uncomfortable answer is yes. And the real question becomes, how many times? The Silurian hypothesis forces us to confront the possibility that we might be just one in a series, not the first civilization of Earth, but the latest in a cycle of rise, flourish, and oblivion. It challenges the comforting narrative of uniqueness, and it warns us that civilizations might not be as durable as we like to believe. Think about what this means. If others have come before, and they are gone, then we too could disappear, swallowed by the same planetary forces that erased them. For all our power, we are not exempt from the rules of geology. Our species could build wonders, climb to the stars, and still be reduced to a whisper in the rocks, a chemical spike in an ancient sediment core, long after the last of our works has turned to dust. But perhaps, somewhere, there is a place where the planet's erasing hand is weak, a refuge where the traces of deep-time civilizations might still hide, waiting for the right eyes and the right tools to find them. The hunt begins with understanding what kind of signals could endure. In the next segment, we'll dive into the planet's memory system and why it is so tragically short. We'll see how the Earth itself, through the slow grinding of tectonic plates and the constant erosion of wind and water, wipes its own slate clean over and over again. And maybe, just maybe, we'll see where it might have slipped up.
If cities crumble, metals corrode, and oceans swallow continents, what could possibly remain? What kind of evidence can resist the slow grind of geological time? The answer is not in skyscrapers or monuments. It is in signatures, subtle, stubborn traces that cling to the planet's memory even when everything else is gone. Imagine standing in a desert where no human foot has ever stepped. You kneel and pick up a rock. Smooth, ordinary, unremarkable. But inside that rock, locked away in its mineral lattice, could be the chemical ghost of an industry that ended before mammals ever walked the earth. To find those ghosts, we need to think like geologists. We need to ask what kinds of materials can survive the planet's relentless recycling, and for how long? Some materials are naturally resistant to decay. Take diamond, for example. Pure carbon arranged in one of the most stable atomic structures in nature. Diamonds don't rust, they don't dissolve easily, and they can survive for billions of years unless subjected to extreme heat deep within the mantle. An ancient civilization might have used industrial diamonds in tools, machines, or precision equipment. Even after the devices themselves were gone, microscopic diamond fragments could still be trapped in sediments. Then there are advanced ceramics. Materials like silicon carbide or titanium carbide are incredibly hard, heat-resistant, and chemically stable. They're used today in cutting tools, aerospace engineering, and nuclear reactors. Over millions of years, they might fracture, they might be buried, but they wouldn't simply vanish. If ancient engineers discovered similar materials, the shards could still be waiting for us, buried under layers of stone, indistinguishable from natural minerals unless examined under a microscope. Another candidate? Metallic glasses. These are alloys cooled so rapidly that their atoms don't have time to arrange into crystals, creating an amorphous structure that resists corrosion far better than ordinary metals. Modern science only recently learned to make them, but if a past civilization had similar metallurgy, fragments might persist as strange, glass-like slivers in ancient strata. But physical durability is only one path to survival. The other is chemical fingerprints, changes in the environment that cannot be explained by natural processes alone. For example, consider isotopic anomalies. Our industrial age has already begun altering the balance of certain isotopes in the environment. Carbon-12 and carbon-13, for instance, are stable isotopes of carbon found in all living things. But when we burn fossil fuels, carbon from ancient life, we release carbon with a distinctive isotope ratio into the atmosphere. That ratio gets locked into sediments, shells, and even ice cores. Now imagine an ancient civilization burning vast amounts of fossil carbon 100 million years ago. Long after their cities and machines vanished, the isotope signal in the rocks would remain, a subtle chemical scar telling us that, for a brief geological moment, something was burning fuel on an industrial scale. It's not just carbon. Industrial activity can concentrate elements in ways nature rarely does. Consider heavy metals like lead, mercury, and cadmium. Smelting and mining scatter these elements into the environment, where they bind to soils and sediments. Over time, they might diffuse, but distinct peaks in concentration could persist in specific layers of rock, hinting at ancient pollution. Even synthetic chemicals could survive, at least as molecular fossils. Some industrial compounds, like certain fluorinated chemicals, resist breakdown for thousands or even millions of years. They might become incorporated into clays or sediments, preserved as chemical curiosities that no volcano, meteorite, or ocean current could produce naturally. The durability of these signals depends on where they end up. A fragment of ceramic dropped on a riverbank might erode in centuries. But the same fragment buried in an anoxic mud at the bottom of a stagnant lake could last for tens of millions of years, protected from oxygen and mechanical disturbance. This is why geologists treasure certain environments as natural archives. Deep ocean sediments, slow accumulating, often undisturbed for millions of years. Peat bogs and anoxic swamps, rich in organic preservation. Caves, sealed chambers that shield artifacts from wind, rain, and temperature swings. Polar ice, capable of preserving atmospheric samples in bubbles for hundreds of thousands of years. If we were to search for the remains of a civilization older than humanity, these are the vaults we would open first. But the search would not be simple. We're not looking for statues or tools. We're looking for anomalies, data points that stand out from the geological background noise. Imagine drilling a core from the ocean floor and seeing, at a certain depth, a sudden, sharp spike in copper concentration, or a strange ratio of isotopes that matches no known natural process. At first, it might seem like an error, contamination perhaps, but if it appears in multiple samples from multiple places around the world, you have a mystery. And mysteries in science are where revolutions begin. The Silurian Hypothesis suggests that if there was a civilization before us, the most likely things we'll find are these kinds of geological puzzles: unexplained chemical shifts, unusual mineral deposits, subtle material fragments. They will not announce themselves as artificial. We will have to suspect, to test, and to rule out every natural explanation before we dare whisper the word civilization. It's worth remembering, even if we found such evidence, proving its origin would be almost impossible. A spike in carbon isotopes could be from fossil fuel burning, or from a massive natural coal fire. An unusual metal concentration could come from ancient mining or from a meteorite impact. The Silurian Hypothesis is not just about the evidence. It's about the detective work, about developing the tools, methods, and mindset to tell the difference between nature's anomalies and civilization's fingerprints. And here lies the deeper implication. We could be standing on top of such evidence right now, mislabeling it in our databases, dismissing it as an odd quirk of ancient geology. The truth could be hidden in plain sight if only we knew how to read it. So the question becomes, how do we separate the signals from the noise? What counts as an industrial fingerprint, and what is just the planet doing what planets do? To answer that, we need to focus on one of the most telling markers of civilization's impact: carbon. On Earth, life has always cycled carbon between the air, the oceans, and the rocks in predictable ways. But when a civilization starts digging up ancient carbon and burning it, the signal it leaves behind in the geological record is sharp, unnatural, and unmistakable if you know where to look. In the next segment, we'll dig deep into this idea. We'll follow the trail of carbon shadows, the isotope scars that an ancient industrial age could have left behind in the rocks. Because if there were others before us, this could be the strongest clue they ever left behind.
If cities crumble, metals corrode, and oceans swallow continents, what could possibly remain? What kind of evidence can resist the slow grind of geological time? The answer is not in skyscrapers or monuments. It is in signatures, subtle, stubborn traces that cling to the planet's memory even when everything else is gone. Imagine standing in a desert where no human foot has ever stepped. You kneel and pick up a rock, smooth, ordinary, unremarkable. But inside that rock, locked away in its mineral lattice, could be the chemical ghost of an industry that ended before mammals ever walked the earth. To find those ghosts, we need to think like geologists. We need to ask, what kinds of materials can survive the planet's relentless recycling? And for how long? Some materials are naturally resistant to decay. Take diamond, for example. Pure carbon, arranged in one of the most stable atomic structures in nature. Diamonds don't rust, they don't dissolve easily, and they can survive for billions of years unless subjected to extreme heat deep within the mantle. An ancient civilization might have used industrial diamonds in tools, machines, or precision equipment. Even after the devices themselves were gone, microscopic diamond fragments could still be trapped in sediments. Then there are advanced ceramics. Materials like silicon carbide or titanium carbide are incredibly hard, heat-resistant, and chemically stable. They're used today in cutting tools, aerospace engineering, and nuclear reactors. Over millions of years, they might fracture, they might be buried, but they wouldn't simply vanish. If ancient engineers discovered similar materials, the shards could still be waiting for us, buried under layers of stone, undistinguishable from natural minerals unless examined under a microscope. Another candidate, metallic glasses. These are alloys cooled so rapidly that their atoms don't have time to arrange into crystals, creating an amorphous structure that resists corrosion far better than ordinary metals. Modern science only recently learned to make them. But if a past civilization had similar metallurgy, fragments might persist as strange glass-like slivers in ancient strata. But physical durability is only one path to survival. The other is chemical fingerprints, changes in the environment that cannot be explained by natural processes alone. For example, consider isotopic anomalies. Our industrial age has already begun altering the balance of certain isotopes in the environment. Carbon-12 and carbon-13, for instance, are stable isotopes of carbon found in all living things. But when we burn fossil fuels, carbon from ancient life, we release carbon with a distinctive isotope ratio into the atmosphere. That ratio gets locked into sediments, shells, and even ice cores. Now, imagine an ancient civilization burning vast amounts of fossil carbon 100 million years ago. Long after their cities and machines vanished, the isotope signal in the rocks would remain, a subtle chemical scar telling us that, for a brief geological moment, something was burning fuel on an industrial scale. It's not just carbon. Industrial activity can concentrate elements in ways nature rarely does. Consider heavy metals like lead, mercury, and cadmium. Smelting and mining scatter these elements into the environment, where they bind to soils and sediments. Over time, they might diffuse, but distinct peaks in concentration could persist in specific layers of rock, hinting at ancient pollution. Even synthetic chemicals could survive, at least as molecular fossils. Some industrial compounds, like certain fluorinated chemicals, resist breakdown for thousands or even millions of years. They might become incorporated into clays or sediments, preserved as chemical curiosities that no volcano, meteorite, or ocean current could produce naturally. The durability of these signals depends on where they end up. A fragment of ceramic dropped on a riverbank might erode in centuries, but the same fragment buried in the anoxic mud at the bottom of a stagnant lake could last for millions of years, protected from oxygen and mechanical disturbance. This is why geologists treasure these environments as natural archives. Deep ocean sediments, slow accumulating, often undisturbed for millions of years. Peat bogs and anoxic swamps, rich in organic preservation. Caves, sealed chambers that shield artifacts from wind, rain, and temperature swings. Polar ice, capable of preserving atmospheric samples in bubbles for hundreds of thousands of years. If we were to search for the remains of a civilization older than humanity, these are the vaults we would open first. But the search would not be simple. We're not looking for statues or tools. We're looking for anomalies, data points that stand out from the geological background noise. Imagine drilling a core from the ocean floor and seeing at a certain depth a sudden, sharp spike in copper concentration, or a strange ratio of isotopes that matches no known natural process. At first, it might seem like an error, contamination perhaps. But if it appears in multiple samples from multiple places around the world, you have a mystery. And mysteries in science are where revolutions begin. The Silurian hypothesis suggests that if there was a civilization before us, the most likely things we'll find are these kinds of geological puzzles: unexplained chemical shifts, unusual mineral deposits, subtle material fragments. They will not announce themselves as artificial. We will have to suspect, to test, and to rule out every natural explanation before we dare whisper the word civilization. It's worth remembering, even if we found such evidence, proving its origin would be almost impossible. A spike in carbon isotopes could be from fossil fuel burning or from a massive natural coal fire. An unusual metal concentration could come from ancient mining or from a meteorite impact. The Silurian hypothesis is not just about the evidence. It's about the detective work, about developing the tools, methods, and mindset to tell the difference between nature's anomalies and civilization's fingerprints. And here lies the deeper implication. We could be standing on top of such evidence right now, mislabeling it in our databases, dismissing it as an odd quirk of ancient geology. The truth could be hidden in plain sight if only we knew how to read it. So the question becomes, how do we separate the signals from the noise? What counts as an industrial fingerprint, and what is just the planet doing what planets do? To answer that, we need to focus on one of the most telling markers of civilization's impact: carbon. On Earth, life has always cycled carbon between the air, the oceans, and the rocks in predictable ways. But when a civilization starts digging up ancient carbon and burning it, the signal it leaves behind in the geological record is sharp, unnatural, and unmistakable, if you know where to look.
In the next segment, we'll dig deep into this idea. We'll follow the trail of carbon shadows, the isotope scars that an ancient industrial age could have left in the rocks.
Every civilization leaves a shadow. Some shadows are written in stone, some in steel, and some in the invisible patterns of atoms themselves. If an ancient industrial civilization once rose and fell on Earth, its most enduring fingerprint might not be its cities or machines, but the chemical scar it left in the planet's carbon cycle. We call these carbon shadows, isotope ratios frozen in rock and ice long after the smoke has cleared. To understand why this is such a powerful clue, we need to remember that carbon is not all the same. It comes in different forms, isotopes. Atoms with the same number of protons, but different numbers of neutrons. Two of these isotopes, carbon-12 and carbon-13, are stable and occur naturally. But here's the key. Living organisms prefer carbon-12. During photosynthesis, plants absorb slightly more carbon-12 than carbon-13, which means all organic matter, from leaves to coal to crude oil, has a distinct, lighter isotope signature. When we humans burn fossil fuels, we're taking carbon that's been locked away underground for millions of years, carbon with that light, organic signature, and dumping it back into the atmosphere. The result is a measurable shift in the ratio of carbon-12 to carbon-13 in the air, the oceans, and the sediments. It's happening right now. If future geologists, 100 million years from now, were to drill into the layers we're creating today, they would see it instantly. A sharp, unnatural drop in carbon-13 levels happening over just a few centuries. This sudden global chemical change is unlike most natural events. Volcanoes, for example, release carbon, but their isotope signature is different, heavier, more balanced. Ocean upwelling events release carbon from deep waters, but again, the pattern is not the same. Burning fossil carbon is unique. It's like signing your name on the atmosphere with invisible ink that lasts for millions of years. Now, imagine this scenario. 50 million years ago, long before humans existed, a civilization arises. They dig, they mine, they burn. They power their world with ancient carbon just as we do now. Over centuries, the isotope balance of their atmosphere shifts. It's recorded in the shells of marine plankton, in the sediments at the bottom of lakes, in the chemical archives of peat bogs and swamps. Then, for whatever reason, they vanish. Cities crumble. Nature heals the scars on the surface, but the isotope anomaly remains, locked in stone, waiting for someone else, perhaps us, to notice it. We already know that Earth's geological record contains dramatic isotope events. One of the most famous is the Paleocene-Eocene thermal maximum, or PETM, about 56 million years ago. During the PETM, global temperatures spiked by 5 to 8 degrees Celsius in just a few thousand years. At the same time, the carbon isotope record shows a massive influx of light carbon into the atmosphere and the oceans, just like the kind we see from burning fossil fuels. What caused it? The leading theories involve natural events, perhaps a colossal release of methane from deep-sea clathrates, frozen methane trapped under the ocean floor. Perhaps volcanic activity that ignited massive coal beds, or some combination of both. But here's the uncomfortable question. If an ancient industrial civilization had burned enough carbon to trigger such an event, would the geological record look any different? The truth is, maybe not. And that's why the Silurian hypothesis is so provocative. It points to events like the PETM and says, we can't be entirely sure what caused them. The PETM isn't the only suspicious moment in the deep past. There are other, smaller isotope anomalies scattered throughout Earth's history. Brief, sharp spikes in light carbon that don't perfectly match known natural processes. Most scientists attribute these to unusual climate events, volcanic episodes, or biological upheavals. But the Silurian hypothesis tells us to keep an open mind, not to jump to alien or prehistoric industry explanations, but to ask whether the patterns we see could, in principle, have been caused by something like us, only much, much earlier. Of course, carbon isotopes are only part of the puzzle. If an ancient industrial age burned carbon, it might have also left behind companion signatures. For example, methane anomalies. Massive, rapid increases in atmospheric methane could indicate fossil gas burning or industrial release. Nitrogen shifts. Large-scale agriculture releases nitrogen compounds that can alter sediment chemistry. Trace metals. Industrial combustion can scatter lead, mercury, and other metals in measurable ways. If we ever found a layer in the geological record where carbon isotope anomalies coincided with these other signals, the case for industrial cause would become much stronger. But here's the challenge. Even with all our modern technology, detecting these ancient signals is incredibly difficult. Sediments mix. Chemical traces blur over time. We may only have tiny fragments of the original pattern, enough to hint, but not enough to prove. And proving it is the hardest part, because extraordinary claims, like the existence of a civilization before humanity, require extraordinary evidence. The Silurian hypothesis doesn't claim that such civilizations definitely existed. It claims that if they did, their chemical shadows might be the only thing left to find. And if that's true, we may already be standing over their graves without knowing it.
Carbon shadows can whisper of fire and fuel, but metals can sing. If an ancient civilization ever mastered mining and metallurgy, they may have left behind traces that no mountain building, no ice age, no hurricane could completely erase. These are the metal ghosts, chemical fingerprints of industry that linger long after the people who made them are gone. Let's start with something simple: concentration. In nature, metals like copper, lead, and silver occur in ore deposits at certain background levels. Mining changes that. When a civilization extracts metals from ore, it produces tailings, waste rock, and soil with altered concentrations of elements. These tailings often contain trace amounts of metals, acids, and other byproducts that don't occur together in those proportions naturally. Over millions of years, erosion will scatter the waste, vegetation will cover it, and tectonics may bury it. But in the right places, like deep sediment layers, or in caves, or in dry, stable soils, these chemical anomalies could persist. They would appear to a geochemist as an odd spike in, say, lead levels, exactly where no natural lead deposit exists.
Some metals are especially telling because they don't like to occur in pure form in nature. Refined aluminum, for example, is extremely rare outside human activity. Bauxite, the ore it comes from, is common, but turning bauxite into aluminum requires enormous amounts of energy. In nature, the metal quickly oxidizes back into minerals. If you found microscopic flecks of metallic aluminum in a 100-million-year-old sediment layer, your first question would be, how did it get here? Volcanoes don't make it. Meteorites contain it only in trace amounts. If it's there in quantity, someone or something must have put it there. Even more revealing are the so-called technology metals, rare elements used in advanced electronics and engineering. Think of tantalum, niobium, and rare earth elements like neodymium and dysprosium. In nature, they occur in low concentrations, scattered across large areas. Industrial civilization concentrates them into mines, factories, and eventually into products like permanent magnets, batteries, and high-strength alloys. When these products break down, the elements don't vanish. They settle into sediments, bind with clays, or sink into anoxic environments where they can remain unchanged for millions of years. A sudden global appearance of high rare earth concentrations in the rock record, coinciding with other industrial signals, would be a serious red flag. And then there are synthetic alloys, combinations of metals that nature almost never produces. Stainless steel, for instance, is an alloy of iron and chromium in proportions not found in any known natural deposit. Superalloys like Inconel or Hastelloy mix nickel, cobalt, chromium, and other metals in precise ratios designed for extreme environments. Even if these alloys corrode, they leave behind a residue with the same unusual ratios, an unmistakable industrial signature. Let's imagine an ancient city. Its towers are clad in copper and steel. Its infrastructure uses kilometers of aluminum cable. Its industries pour molten alloys into molds, forging machines and weapons. Then, the civilization collapses. The buildings fall. Metals corrode into dust. Wind and water scatter the dust into rivers and floodplains. Centuries pass. Then millions of years. By now, the city is gone. The continent itself may have drifted to a new position, but deep underground, in the layered archives of ancient riverbeds, there is a band of sediment with odd metal concentrations: iron, chromium, nickel, aluminum, rare earths, all peaking sharply in a thin slice of geological time. It's the only surviving trace of a technological age. We know this is possible because we've already seen something similar from ourselves. In the modern world, industrial pollution is leaving behind what geologists call anthropogenic layers, strata that contain elevated levels of metals and other byproducts of technology. We see it in lake sediments near mining towns, where heavy metal levels spiked sharply in the last century. We see it in deep-sea mud, where industrial emissions have deposited a measurable layer of lead and mercury. If our civilization vanished tomorrow, these layers would persist. Over millions of years, they might thin and spread, but the anomalies would remain detectable, a metallic ghost embedded in the rock. And then there's the possibility of ancient mining scars. Mining often leaves behind telltale alterations in the geology: collapsed tunnels, altered mineral seams, and chemical residues that differ from untouched rock.
Even if the tunnels collapse and the rock recrystallizes over millions of years, the geochemical differences could persist. A trained geologist could detect that the deposit had been disturbed, mined, long after any physical structure was gone. But here's the twist. Sometimes these metallic ghosts could be misread. Nature can create metal anomalies too. Meteorite impacts can scatter rare metals across large areas. Volcanic eruptions can concentrate certain elements in ash layers. Hydrothermal vents can create strange metal-rich deposits on the sea floor. The challenge is telling the difference. A single anomaly might be explained away as natural, but if you find multiple anomalies, the same metal concentrations at the same time in widely separated places, that starts to look less like geology and more like technology. So if we were serious about testing the Silurian hypothesis, one strategy would be to map the global distribution of metal anomalies in the rock record. Cross-reference them with isotope changes, synthetic material traces, and other unusual signals. If the patterns line up, you may have found more than just a curious mineral deposit. But metals aren't the only thing that could be left behind. Sometimes the most important clues are what's missing: the silence in the fossil record, the sudden disappearance of certain species, or the absence of expected minerals. Because an advanced species wouldn't just leave behind its own creations, it could also leave behind the scars of its impact on the biosphere. In the next segment, we'll explore the silence of the fossil record and how the absence of evidence can sometimes be evidence itself. We'll see how an advanced species could live and die without leaving a single skeleton, and why that might be the most chilling possibility of all.
When most people imagine finding an ancient civilization, they think of skeletons, statues, tools, the solid, tangible remnants of a life once lived. But in the deep timeline of the Earth, those things are almost never preserved. The fossil record is not a complete book. It is a torn, water-stained journal with most of its pages missing. What survives is not a fair representation of the past. It is a biased, selective memory, and most of what has happened on Earth has been lost forever. Let's start with the basics. Fossilization is rare, extremely rare. In fact, the overwhelming majority of living things that have ever existed have left no fossil at all. Here's why. For a body to fossilize, it needs an almost impossible sequence of events. First, the organism has to die in a place where it won't be eaten or decomposed right away, somewhere with rapid burial in sediment, like a river delta, a floodplain, or the seafloor. Then, over time, minerals must slowly replace the organic material, turning the bones or shells into stone. And even after all that, the fossil has to survive millions of years of geological upheaval without being eroded, crushed, or melted. Most environments simply don't meet those conditions. Forests, mountains, deserts, the places where civilizations might thrive, are some of the worst environments for fossil preservation. Now add another factor. Civilizations are small in the grand scheme of things. Even today, our urban areas make up less than 1% of Earth's land surface. If you were to erase us tomorrow, the odds of a paleontologist in 100 million years finding a fossilized human skeleton in the tiny fraction of the planet we've occupied are vanishingly small. If an ancient civilization was like ours, spread thin across continents, concentrated in cities, their remains would be even harder to find. And here's a sobering truth. We've only explored a fraction of the fossil-bearing rocks on Earth. Most paleontological work happens in certain accessible layers and locations, leaving vast areas and potentially vast eras untouched. If the fossils of a prior civilization exist, they could easily be buried in unexcavated rock layers, locked under kilometers of sediment, or subducted into the mantle long ago. There's also the problem of recognition. Even if we found a fossil from a hypothetical pre-human civilization, would we recognize it for what it was? Consider this. Many intelligent life forms might not look human at all. They could be reptilian, avian, aquatic, or something so unlike us that we might mistake them for an unusual animal species. A single skull without context might end up in a museum drawer labeled as an unknown extinct reptile or unusual mammal, never connected to the idea of an advanced society. Then there's the issue of artifacts. Stone tools can last for millions of years, but only if they are in the right conditions, and even then, their survival is mostly a matter of luck. Metal tools, wood, cloth, paper, they vanish on human timescales, let alone geological ones. Even baked clay or fired bricks crumbled into dust given enough time. The Great Pyramids, as massive as they are, will eventually erode away entirely. The tallest skyscrapers will fall and vanish in a blink of geological time. This means that absence of evidence is not evidence of absence. The fact that we haven't found any clear artifacts from a civilization older than ours doesn't prove they never existed. It may simply mean that the planet has hidden them too well, or erased them entirely. The fossil record's silence could be the result of natural filters, the rarity of fossilization, the limited area civilizations occupy, the relentless recycling of Earth's surface. It could also be the result of us not knowing where or how to look. And here's the haunting part. Even our own species could vanish from the fossil record with barely a whisper. If humanity were to disappear today, and if our remains were scattered in the environments we live in now, only a tiny fraction of our skeletons would ever fossilize. Most of our bones would be destroyed within centuries. Our artifacts would follow, leaving behind only the chemical traces, the ghosts we talked about before, in rock and soil. A paleontologist in 100 million years might find a thin layer with unusual isotopes, strange metal concentrations, and a few ambiguous fossils. Would they conclude that a technological civilization once existed? Or would they chalk it up to a strange natural event and move on? This is why the Silurian hypothesis is so unsettling. It doesn't require that ancient civilizations existed. It only points out that if they did, the fossil record might never reveal them. In that case, our only hope is indirect evidence, the geochemical clues, the subtle markers in stone and sediment that speak for the vanished. But yet there is one place on Earth that might preserve the remains of a civilization better than most: the ocean floor. It's not because the ocean floor is old. In fact, most of it is geologically young. It's because certain parts of it can act as a cold anoxic vault, burying and sealing away whatever falls there. If we want to find traces of civilizations long erased from the land, we may need to look beneath the waves. In the next segment, we'll dive into the deep, to the strange, slow landscapes of the seafloor, to see how the oceans could hide the last surviving clues to an ancient world.
If the continents are restless and forgetful, the oceans are even more ruthless. The seafloor is not a place where history lingers. It is a conveyor belt, endlessly consuming itself. But there are places in the deep where time slows down, places where the past can rest undisturbed for tens of millions of years. And if an ancient civilization ever existed, the last whispers of its story may lie in these hidden vaults beneath the waves. First, the bad news. Most of the ocean floor is young, very young. Because of plate tectonics, new crust is constantly forming at mid-ocean ridges and being destroyed in deep trenches. On average, the seafloor is less than 200 million years old, a blink in geological time. If a city once stood on land that is now under the ocean, and that land has since been subducted, it's gone forever, swallowed by the mantle. But not every part of the ocean shares this fate. Some regions, especially those far from subduction zones, can hold their sediments for extraordinary lengths of time, and it is in those sediments that secrets might survive. Picture the abyssal plains, vast flat expanses of seafloor thousands of meters below the surface. Here, life is sparse, currents are weak, and sediment rains down slowly from above. Microscopic shells, dust from continents, even particles from meteorites. Over millions of years, this rain forms layers so fine you could count them like tree rings. Each layer is a page in the ocean's diary, recording changes in climate, biology, and chemistry. If debris from an ancient civilization, fragments of ceramics, bits of metal, microscopic glassy beads from industry ever reached these depths, it could be buried within weeks. And once buried in the cold, oxygen-poor mud, it might stay there indefinitely. There's also the deep anoxic basins, rare places where oxygen is absent from the bottom waters. In these environments, decay slows to a crawl. Organic materials that would rot away on land, textiles, wood, even delicate structures, could survive far longer. Modern examples include parts of the Black Sea, where ancient shipwrecks have been found nearly intact after more than 2,000 years. Now stretch that preservation potential across millions of years, with slow burial under fine sediments, and you begin to see why the deep ocean could be a time capsule for traces of ancient technology. But there's a problem. Getting to these archives is hard. The deep sea is vast, dark, and hostile. Even with modern technology, we've explored less than a fraction of it. Drilling cores from the abyssal plains is expensive and time-consuming, and most are taken for climate studies, not for hunting the fingerprints of lost civilizations. If ancient traces are down there, we might already have drilled through some of them without even noticing. Tiny metallic particles, odd isotopic shifts, unusual mineral fragments, all could be misinterpreted as natural if we're not looking for industrial causes. And here's an intriguing thought. Some industrial materials are denser than natural sediments. That means they might sink deeper into the seabed, even piercing through soft layers until they lodge in harder strata below. These could be fragments of heavy alloys, ceramic components from high-temperature reactors, or even parts of spacecraft that fell back to Earth. If buried deep enough, they could be shielded from chemical breakdown for immense spans of time. There's also the possibility of geological traps on the seafloor. Underwater landslides, volcanic ash falls, or sudden sediment avalanches can bury objects instantly, sealing them off like Pompeii beneath the waves. Such events could preserve not just fragments, but potentially entire structures, though the odds are slim, and finding them would be like searching for a single coin in the world's largest desert. But maybe there's another approach. Instead of just looking on Earth, we could search for ancient traces where geology is frozen in place, a world where erosion and plate tectonics don't erase history. And there is one such place, close enough for us to reach, our own moon. Because if an ancient civilization ever reached space, even briefly, it might have left artifacts there, undisturbed for millions or even billions of years. And unlike the ocean floor, the moon doesn't recycle its surface. There are no winds, no rain, no tectonics. A footprint can last for millions of years. A spacecraft fragment could last for eons. But before we leave Earth entirely, there's still one more cold archive to explore. One that is not under the sea, but locked in the frozen heart of the poles. In the next segment, we'll journey to the polar vaults, the ice sheets of Antarctica and Greenland, to see how these frozen archives could hold chemical clues to civilizations no one remembers. Because while the deep sea is a time capsule, ice can be a magnifying glass, preserving the chemistry of ancient air drop by drop, year by year.
The poles are the planet's locked vaults. Antarctica, and Greenland, frozen continents that guard a secret archive, not of bones or buildings, but of air itself. For hundreds of thousands of years, snow has fallen here, layer upon layer. Each winter's snow traps tiny bubbles of the atmosphere, sealing them inside as the weight above compresses the snow into ice. Year after year, century after century, the ice thickens, stacking time like pages in a book. And within those bubbles is a chemical diary of the world. When scientists drill ice cores from the polar caps, they are reading this diary. Each layer contains the exact composition of the atmosphere when it formed: carbon dioxide levels, methane concentrations, traces of volcanic ash, even hints of industrial pollution. From these frozen cylinders of ice, we can reconstruct ancient climates, detect massive volcanic eruptions, and even track the rise and fall of civilizations in recent millennia. But what if the ice could also reveal the fingerprints of a civilization so old that no human memory reaches it? Here's the key. If an ancient industrial civilization burned fossil fuels, released synthetic chemicals, or altered the composition of the atmosphere in any large-scale way, those changes could be captured in polar ice, provided the civilization existed during a glacial period. Just like our own Anthropocene spike in carbon dioxide will be visible in ice for millions of years to come, their industrial signature could be preserved as a sharp, unnatural chemical shift in an ancient ice layer. The challenge, of course, is survival. Ice is not eternal. Antarctic ice sheets can preserve atmospheric records going back more than 800,000 years. Greenland's record is shorter, around 120,000 years. Beyond that, ice is lost to melting, flow, and sublimation. Over millions of years, entire ice sheets vanish during warm periods, taking their atmospheric archives with them. This means that if a civilization existed tens or hundreds of millions of years ago, their air chemistry will not be waiting for us in ice. The ice simply wasn't there then. But that doesn't mean the idea is useless. If we were to discover strange geochemical shifts in ocean or lake sediments from a warm period, finding similar shifts in ancient ice from a subsequent glaciation could act as a crucial confirmation. Proof that the signal wasn't just a local phenomenon, but a global event. But even more tantalizing is the possibility of buried ice. Ancient frozen deposits trapped deep under rock or sediment, protected from melting through geological luck. Such ice has been found in rare places on Earth, in permafrost, beneath volcanic ash layers, and inside mountain glaciers. If by some improbable chance a deposit of multi-million-year-old ice exists, it could be the closest thing we have to a time machine for the atmosphere. If the Earth is forgetful, the Moon remembers everything. No wind, no rain, no plate tectonics, no rivers to carve valleys, no glaciers to grind mountains down. On the moon, a footprint can last for millions of years. A piece of metal can survive for billions. It is, in every sense, the perfect archive. Here's why this matters. If a civilization ever reached space, even briefly, and sent spacecraft to the moon, the traces of their visits might still be there today. Think about our own presence. We've left landers, rovers, flagpoles, tools, and even bags of trash on the lunar surface. If humanity vanished tomorrow, those objects would slowly degrade under the relentless bombardment of micrometeorites and radiation. But they wouldn't be swept away. They'd simply fade, molecule by molecule over eons. Even after 1 billion years, the shape of a lander might still be visible, though pitted and scarred by impacts. Unlike Earth, where geological processes bury and erase, the moon's only weather is from space. Micrometeorites, tiny impacts that sandblast surfaces over time. Solar wind, streams of charged particles that gradually alter exposed materials. Cosmic rays, high-energy radiation that breaks down complex molecules. But these processes are slow, painfully slow. A metal plate left on the moon today could survive for tens of millions of years before becoming unrecognizable. A buried object could last much, much longer. This means that if a spacefaring civilization visited the moon at any point in the last 1 billion years, we might still find their hardware, or at least fragments of it, lying in the dust. It could be an automated probe, a crewed lander, a scientific instrument array, or even a monument, something placed deliberately to last. Of course, there's a problem. The moon is huge. Its surface area is about the size of Africa, and we've only explored tiny portions of it in detail. Most of it remains unphotographed at high resolution, and even in the areas we've imaged, small objects can be hard to spot. A probe the size of a car could be hidden in a crater shadow, its surface dulled to match the regolith. A buried artifact might be invisible except to radar or ground-penetrating sensors. There's also the question of time frames. If an ancient civilization existed hundreds of millions of years ago, the moon would still have been geologically quiet. But over that long a period, micrometeorite impacts could erode even large artifacts down to shapeless lumps. The longer the gap, the harder it becomes. But it's not impossible. Some materials, especially ceramics or metallic alloys engineered for durability, could survive in recognizable form far longer than most metals. Then there's the tantalizing possibility of subsurface preservation. If an object were deliberately buried on the moon, either to protect it from impacts or to hide it, it could be shielded from erosion almost indefinitely. It might be hidden just a few meters of regolith, waiting for a rover, drill, or unlucky astronaut to stumble across it. Imagine uncovering something that's clearly not a rock, a machined component, an alloy plate, a carved symbol, lying in pristine condition after hundreds of millions of years in the dark. And this idea isn't just speculation. We already use the moon as an archive. In 2019, a private lunar lander called Bereshit carried a lunar library, a tiny archive containing human knowledge intended to last for billions of years. It crashed on landing, but the payload may still be intact, preserved in the vacuum. If we think that's a good way to send a message forward in time, why wouldn't a past civilization have thought the same thing? Searching for such evidence would require a deliberate program. high-resolution imaging of the lunar surface, radar scans for buried anomalies, targeted landings in areas with unusual shapes or reflectivity, and crucially, the willingness to consider that not every odd shape is a boulder. But what if a civilization went further than the moon? What if they left objects not just on nearby worlds, but drifting in space itself? Because out there, in the vacuum between planets, time slows almost to a stop. A well-built artifact in a stable orbit could last for hundreds of millions of years, untouched, unweathered, unchanged. In the next segment, we'll leave the moon behind and head out into the darkness to explore the idea of extraterrestrial time capsules. We'll see how ancient probes, stations, or even derelict spacecraft could still be orbiting quietly in our solar system, and how we might find them.
In the vacuum of space, time slows to a crawl. There are no winds to wear away surfaces, no oceans to corrode metal, no shifting crust to swallow history. An object placed in a stable orbit around the sun could, in theory, last for hundreds of millions, even billions of years. And if an ancient civilization once reached beyond Earth, the most enduring relics of their existence might be floating out there still, silent, invisible, waiting to be found. Space is the ultimate preservation chamber. Without oxygen, rust cannot form. Without water, corrosion is impossible. Without an atmosphere, there's no weather, only the slow patter of micrometeorites and the constant but gentle bombardment of solar and cosmic radiation. Yes, those forces will eventually degrade anything, but they do so on unimaginably long timescales. A spacecraft in deep space, far from planets and debris fields, could remain intact for geologic ages. We can imagine several kinds of extraterrestrial time capsules. Derelict spacecraft in stable solar orbits, artificial satellites placed around planets or moons, probes intentionally parked in asteroid belts or Trojan points for safety, monuments or beacons designed to broadcast a signal until their power fails, and then remain as silent markers. The key to longevity in space is orbit stability. Most objects in low Earth orbit eventually spiral back into the atmosphere. But a spacecraft in a solar orbit between Earth and Mars could remain undisturbed for eons. Similarly, placing an artifact in a Lagrange point, a gravitationally stable position, could keep it in place for as long as the sun itself burns. Our own civilization has already seeded such artifacts. The Voyager probes, launched in 1977, now coasting into interstellar space with golden records aboard. The Pioneer probes, each carrying a plaque depicting our place in the galaxy. The New Horizons probe, which flew past Pluto and now drifts quietly in the Kuiper Belt. If humans vanished tomorrow, these probes could still be found millions of years from now. Any species that discovered them would instantly know they were artificial. They are too symmetrical, too engineered, too precise to be natural. Now imagine reversing the situation. What if, somewhere in the asteroid belt or in a Trojan point, there's an ancient probe that isn't ours? A derelict craft from a civilization that vanished before humans ever existed. It might be tumbling slowly in the dark, covered in a thin patina of micrometeorite scars. Its systems would be dead, its transmitters silent. But the design, the materials, the geometry, all would betray its artificial origin.
You might think, surely we would have noticed something like that. But the truth is, we've barely looked. The solar system is vast, and our surveys focus mostly on objects that pose a danger to Earth. Small, dark, non-reflective artifacts could easily escape detection, especially if they're parked far from planetary light. Some researchers have even suggested that unusual objects like Oumuamua, the strange interstellar visitor detected in 2017, might be worth considering in this context, though the mainstream view remains that it was a natural body. Still, the possibility lingers in the back of the mind. There's also the idea of passive beacons, devices placed where they would be easy for a future spacefaring civilization to find. A probe parked in a high lunar orbit, an artifact set down on a stable asteroid, something placed deliberately on the easiest to reach surfaces for anyone with rockets. We could check those places. We should check those places, because the odds of a chance encounter are low, but the payoff, if found, would rewrite everything. Here's the paradox. We ourselves are already creating such time capsules. Every probe we've launched beyond Earth is a message in a bottle. And if we, a young, brief-lived species, are doing this now, doesn't it seem possible that others before us might have done the same? Maybe they did. And maybe they expected someone like us to come looking. But if space is one of the best places to preserve technology, then the opposite is true for biology. Life, fragile, complex, carbon-based, rarely survives long without a constant fight against entropy. If we want to find a deeper kind of evidence, not just machines but the living world that made them, we must turn our search back to Earth. Not to cities or monuments, but to the very fabric of life itself. Because there's another archive, one that exists in every cell of every creature alive today. DNA. In the next segment, we'll explore genetic echoes, how traces of an ancient civilization might be hidden not in stone or metal, but in the code of life itself. A record that evolution has been writing for billions of years, and that we're only just learning how to read. Stone crumbles, metal corrodes, even the stars burn out. But life carries its own form of memory, a memory written in molecules, a language 4 letters long. We call it DNA. DNA is more than just the instruction manual for building a living thing. It is an unbroken chain of information, passed from generation to generation across billions of years. Every organism alive today is a living archive carrying genetic echoes of everything that came before it. Some of those echoes are ancient, so ancient that they predate humanity, predate mammals, even predate the very idea of complex life. So, here's the question. If a civilization existed millions or hundreds of millions of years ago, could they have left a message or a signature embedded in the code of life itself? The idea is not as far-fetched as it sounds. We are already capable of inserting arbitrary sequences into DNA, sequences that do not affect the functioning of the organism, but which can carry information. In 2012, scientists encoded an entire book into DNA. We've stored images, music, and even short movies inside the genome of living bacteria. If we can do this now, then a civilization millions years more advanced than us could have done it too, perhaps on a planetary scale. Imagine this. A species foresees its own extinction. They want to leave something behind, something that will survive the destruction of cities, the erosion of mountains, the shifting of continents. They choose life itself as the medium. They encode a message, instructions, coordinates, warnings, or even their history into the genomes of long-lived species. Bacteria, which can survive in extreme environments, plants, which cover vast areas of the globe, or even into the germline of complex animals, ensuring the code is passed down for millions of years. Over time, the message would degrade, mutations would scramble it, but with the right redundancy, repetition, error correction, self-repairing structures, it could persist far longer than any physical monument. And here's the unsettling part. We wouldn't necessarily notice it. The genome is full of sequences whose functions are unknown. Much of it is what we call junk DNA, regions that don't code for proteins and which can carry repeated patterns with no obvious biological purpose. If an ancient message exists, it might be hiding there, camouflaged as meaningless noise. We have hints, though, not of alien messages, but of the genome's capacity to carry unexpected signals from the past. Endogenous retroviruses, fragments of ancient virial DNA, make up a significant portion of our genome. These are the fossilized remains of infections that happened tens of millions of years ago, passed down from ancestor to descendant until today. If nature can preserve viral DNA for that long, it could also preserve an artificial sequence if it were designed to last. There's another angle to consider. What if the evidence isn't a message, but a modification? If a past civilization engaged in large-scale genetic engineering, they might have left behind organisms with features that don't make sense in a purely evolutionary context. We're talking about traits too complex, too precisely engineered to arise by random mutation and natural selection alone. In our own time, we've already created genetically modified crops, bioengineered microbes, and lab-grown animals with novel traits. If we vanished, some of these could, in principle, survive and continue passing their engineered genes forward, diluted, altered, but still traceable millions of years later. The search for such genetic echoes would be subtle. It would involve scanning genomes for sequences that defy evolutionary logic, patterns too mathematically precise, or containing encoded information in binary, prime numbers, or other non-natural arrangements. We've barely begun to look. And even if we found such a pattern, proving it was artificial and ancient would be one of the hardest challenges science could face. Still, the thought lingers. Right now, inside every living cell on Earth, there could be fragments of a story written by hands, or claws, or tentacles, long gone. Perhaps they never expected anyone to read it. Perhaps they wrote it for us. But if the genetic record is one possible legacy of a past civilization, there's another that is less elegant and far darker. Because not all legacies are noble. Some are toxic, some are lethal, and some can outlast even life itself.
Civilizations dream of monuments, pyramids, temples, towers that will stand for ages. But sometimes, the most enduring monument is not carved from stone. It's made from poison. Every industrial age leaves behind its waste. For us, it's plastics, heavy metals, synthetic chemicals, and radioactive isotopes. Substances that nature did not produce in such abundance before we came along. And while cities will crumble and monuments will erode, these toxic legacies can linger for millions of years. They may outlast every book, every statue, every memory.
Let's begin with plastics. They are everywhere, in oceans, in soil, in the atmosphere. Strong, lightweight polymers that nature struggles to break down. Over centuries, they fragment into smaller and smaller pieces, microplastics, then nanoplastics, but the molecules themselves can persist far longer. In the distant future, the physical shape of a bottle will be gone, but its chemical fingerprint could still be trapped in sediments, locked into the structure of the rocks themselves. Geologists are already seeing this today. Plastics fused with beach sand and volcanic rock into strange new materials, plastiglomerates, a hybrid of nature and industry that could be preserved indefinitely. Then there are persistent organic pollutants, synthetic compounds like PCBs and DDT. They do not break down easily in the environment. Even in tiny concentrations, they can remain stable for tens of thousands of years. Buried in the right conditions, they could last far longer, becoming a strange chemical spite in the geological record. But perhaps the most chilling toxic legacy is radioactive waste. Our nuclear reactors and weapons programs produce isotopes that simply do not exist naturally in significant quantities. Isotopes like plutonium-239, with a half-life of over 24,000 years. And some, like iodine-129, persist for 15.7 million years. Even after 1 million years, traces of these isotopes would still be detectable, embedded in glassified waste or trapped in the minerals where we tried to store them. If an ancient civilization ever mastered nuclear energy, the telltale isotopic fingerprints of their reactors could still be measurable today, not in ruins, but in rocks. Nuclear detonations also leave a unique geological calling card: trinitite, a green, glassy material formed when sand is fused by the heat of an atomic blast. It contains unusual isotopes, melted minerals, and a structure unlike anything produced by volcanism or meteor impacts. If a layer of trinitite-like material were found in rock millions of years older than humanity, it would be a nearly undeniable sign of technological activity. Heavy metal contamination is another legacy that can endure. Mining and smelting release massive amounts of lead, mercury, cadmium, and other toxic metals into the environment. They do not degrade. They bind to sediments and remain detectable as long as the rock exists. If we were looking for ancient industry, a sudden global spike in heavy metals, synchronized across distant sites, would be a powerful piece of evidence. There's something poetic and tragic about this. We imagine our legacy will be art, culture, knowledge. But in deep time, the most durable traces of our civilization may be its mistakes, the poisons we spread without thinking, the substances we made that the planet cannot recycle. And this raises a haunting thought. What if the reason we find certain strange chemical signatures in ancient rocks is that someone before us made the same mistakes? We already know of events in Earth's history, like the Permian-Triassic extinction, where unusual spikes in carbon dioxide, methane, and certain metals coincide with mass die-offs. We usually blame these on volcanism or asteroid impacts. But could some of them be the echoes of an industrial civilization long gone? Of course, without context, these toxic traces could be dismissed as natural. To be certain, we'd need them to line up with other signs. Synthetic materials, isotopic anomalies, perhaps even fossils of the civilization itself. Which means our search can't focus on just one kind of evidence. It has to be holistic, an investigation that pieces together chemical, geological, and biological clues into a coherent picture. And if we're going to piece together such a picture, we must understand not only what to look for, but why civilizations vanish in the first place. Because the Silurian hypothesis is more than an archaeological mystery. It is also a warning. If other civilizations have risen and fallen before us, the question we should be asking is not only whether they existed, but what destroyed them. In the next segment, we'll turn from evidence to extinction. We'll explore the civilizational cliff, the forces that can drive an advanced species from its peak straight into oblivion.
Every civilization thinks it will last forever. But in the deep ledger of history, even the short human history we know, the climb to the top is followed by a fall. And sometimes, the higher the climb, the steeper the cliff. The civilizational cliff is not just about collapse. It's about acceleration, the way progress can speed a society toward its own end. Technology amplifies power, but it also amplifies risk. The same tools that let you harness energy, reshape landscapes, or reach space can also poison your environment, strip your resources, or ignite conflicts you cannot control. In our time, we know the threats by name. Every civilization thinks it will last forever. But in the deep ledger of history, even the short human history we know, the climb to the top is followed by a fall. And sometimes, the higher the climb, the steeper the cliff. The civilizational cliff is not just about collapse. It's about acceleration, the way progress can speed a society toward its own end. Technology amplifies power, but it also amplifies risk. The same tools that let you harness energy, reshape landscapes, or reach space can also poison your environment, strip your resources, or ignite conflicts you cannot control. In our own time, we know the threats by name: climate change, nuclear war, ecological collapse, unchecked artificial intelligence, pandemics, natural or engineered. But the pattern is older than us. Even a civilization millions of years in the past would have faced its own versions of these dangers, challenges scaled to its level of technology. Some collapses might come suddenly, a chain reaction in weapons systems, a biological catastrophe that spreads too fast to stop, an asteroid impact that coincides with political instability. Others might be slow and invisible, the gradual erosion of soil, the creeping toxicity of water supplies, the loss of biodiversity until agriculture fails. The Silurian hypothesis forces us to consider that the ultimate cause might be both a long decline suddenly tipped into disaster by one decisive blow. We often assume that if a civilization is advanced enough to reach the stars, it will have solved its existential problems. But perhaps the opposite is true. Reaching for the stars requires massive energy use, enormous resource extraction, and unprecedented complexity.
And complexity is fragile. The more interconnected a system becomes, the more ways it can break. If we look at Earth's history, we see abrupt transitions, sudden shifts in climate, chemistry, and life forms. Mass extinctions happen in geological instants, erasing dominant species and reshaping the biosphere. Some were triggered by impacts, some by volcanism, and some we can't explain. Could one of those unexplained extinctions mark the end of a technological age? There's another possibility, one more chilling still. A civilization may see the cliff ahead and still walk off it. Addiction to a certain technology, inability to unite politically, a cultural momentum that refuses to slow down even when the edge is visible. In our own era, we've seen this with fossil fuels. We know the risks, we know the consequences, and yet the machine keeps running faster every year. Now, imagine a civilization 100 times more advanced but trapped in the same psychological patterns. Knowledge alone doesn't guarantee survival. When the fall comes, it can erase a civilization almost completely. Cities decay in decades. Technology rusts, shatters, or is buried in centuries. Within a few thousand years, the surface of the planet can be scrubbed nearly clean. In 1,000,000 years, only the most stubborn traces, the ones we've been discussing, will remain. And so, the Silurian hypothesis is more than speculation. It's a mirror. It asks, if others have climbed this cliff before us and fallen, what makes us believe we will be the ones to survive the drop? Because if the cliff is real, then we too may one day vanish, leaving only a strange spike in the rocks, a few odd isotopes, and a question for whoever comes after us. Were they ever here at all? But before we reach that edge in our own story, there is one more place to look. One more arena where the past may be hiding in plain sight. Not in rocks, not in ice, not in the genome, but in our own myths and memories. In the next segment, we'll explore cultural fossils, the possibility that stories, symbols, and legends might preserve a distorted memory of civilizations so old that they've passed entirely out of history and into myth. Music fades into the low hum of voices, as if coming from far away through time. We have searched in the rocks, in the ice, in the ocean depths and the vacuum of space. We have looked in the code of life and the echoes of our oldest stories. We have asked, what if we are not the first? Now comes the final question. If we found proof that another civilization lived and died long before us, what would it mean for the one we're building now? In one sense, it would be exhilarating to know we are part of a much larger human or post-human story, that intelligence has bloomed here more than once, that the spark is not unique to our age. It would mean that the universe may be more hospitable to life and intelligence than we dared to hope. If it happened before, it could happen again, here and on other worlds. But it would also carry a shadow, because the ruins we'd find would not be thriving cities. They would not be starships in flight. They would be the quiet, fossilized remains of a species that failed to survive its own peak. They would be a warning. In deep time, Survival is not about brilliance. It is about balance. And civilizations, by their nature, disrupt balance. To rise, they must consume resources, energy, ecosystems. To endure, they must learn when to stop. If we found that others had walked this path and fallen, the mirror they would hold up to us would be uncomfortable to look at. We might see ourselves in them, the same overreach, the same overconfidence, the same blind spots. And if they were gone, it would force us to ask whether the cliff is always there, whether every technological species burns too hot, too fast, and collapses before it can stabilize. The Silurian Hypothesis is, at its core, not just a question about the past. It's a thought experiment about our future. It challenges us to imagine our own legacy millions of years from now. What would survive? What would be erased? If another species rose from the ashes, would they know we were here? Or would we be just another layer of strange rock, another chemical spike, another myth of a vanished golden age? Perhaps the most haunting thought is this: if we did find them, if we uncovered undeniable proof of a civilization that lived and died before us, we would also know that intelligence is not enough to ensure survival. And if it wasn't enough for them, why should it be enough for us? But maybe, just maybe, their greatest gift to us would be the chance to do better, to see the cliff ahead of time, to learn the lessons they could not pass on in person, to carry their story into the future, not as a warning unheeded, but as a turning point. In the end, the Silurian Hypothesis is not just about whether they were here. It's about whether we will be here. Whether millions of years from now, the Earth will still hold a living, thriving civilization, or just the silent, stubborn remnants of one more species that could not last. The truth may be waiting for us, in the rocks, in the ice, in the whispered echoes of ancient tales, and perhaps one day, we will find it.